That means if we want to hold data, what is the maximum voltage we can, noise voltage we can tolerate? So we have been looking at that, right? So then now let's look at a read and write case, okay? So SRAM read. SRAM read is done by turning on these access transistors, and you usually pre-charge bit line and bit line bar to some identical value. So let's say you pre-charged these bit line and bit line bar to VDD, and then you turn on these access transistors by driving word line high. So for the other cells, your word line should be 0. But for this cell you want to read, you drive your word line to 1, so that you turn on these MOS transistors here. Then now what's happening here is, if you are storing 0 and 1 here, then this bit line will be discharged through this N2 and N1. Whereas, because this node is driven high, there will be no current flowing through this access transistor, right? So, depending on which side you are storing 0, that side will discharge the bit line. So this voltage will go down like VDD minus. So this node will go down something like this. This node will stay something like this. So you can sense the different voltage difference between these two nodes and then read it out as a digital data. Okay? So here there's another stability issue, which is on this side. Here there's no current flow, so it's not a big deal. But on this side, what happens is, now basically what you have is, you have N2, and initially you have VDD here, and then you have N1 and ground. So this is VDD, this is VDD, so you are discharging your charge on this bit line, right? And now what happens is, this node voltage will initially go up, because for this N1 transistor to pull down current, you need some VDS, right? So for sure, this node voltage will be, initially it was 0, but it should go up a little bit. And that really depends on the internal or equivalent resistance of this NMOS transistor and this NMOS transistor. If your resistance is much smaller here, then this node voltage would go up very little. But if your resistance is much higher on this side, then this voltage would go up a lot. Then that is a problem, because if this node voltage goes up more than a certain amount, then that actually then this node is actually connected to this NMOS transistor. So this could be actually turned on if this node voltage goes up too much, right? Then this could be turned on, this will pull down the output, and this will be 0, this could be on, so your stored value could be flipped. So you have to keep this node A voltage low enough. You should keep it low enough, right? So this is called read offset. If you during the read operation, if you had upset, like data flipped because of this internal node voltage fluctuation, you're losing data. And this is one of the major problems in SRAM. You have to deal with this. So then if we want to think about how this read offset happens, we can simplify the read scenario like the figure shown here. So initially, we originally had this PMOS here, NMOS here, right? But because this was VDD and this was ground, we could assume these are off. Okay, so let's get rid of those and make the simpler diagram like this. Okay, then assuming we are initially storing 0 on the left side and 1 on the right side, again we are discharging bit line through N2 and N1. Okay, so, and I think I already explained too much in earlier slide, and in that case your current is flowing through this path, so what really matters is what is the resistance ratio between this N2 and N1. That determines how high this voltage would go up, right? So we have to think about what is the sizing ratio of this NMOS and this NMOS should be, right? And because we want to minimize the voltage fluctuation on this node A, what we want is we want to make this NMOS on lower side wider and NMOS on this access transistor narrower, weaker, in other words. That will help you preventing read upset, right? So if you actually adjust your sizing ratio, your NMOS ratio, and if you plot that on the x-axis, and if you plot the amount of voltage that rises on the y-axis, it would look like this. So as you make your pull-down NMOS wider, your fluctuation voltage would be smaller. So you actually want to stay on this side for read stability sake. But in other words, that means you are making your, you can, because both of those are NMOS transistors, you can set your access transistor as a minimum size transistor, and you can set your pull-down transistor as non-minimum or wide transistor. But as you make it wider and wider, you're actually increasing your cell area. So you can't just keep making it wider. So you should, the SRAM designers should find like reasonable ratio for these NMOS transistors. So you don't want to go too wide for the area minimization, but you don't want to stay around 1 because you want to make sure you can prevent this read offset. So there's that trade-off. Okay. Okay, then we can use VTC again to think about what is the noise margin during the read operation. So this gives you a different way of view for the read operation. So during the read operation, what we are doing is we pre-charge both bit line to VDD initially, and then turn on these access transistors. So right after this, right after turning on this access transistor, what we see on this node and this node is actually VDD, right? Because both our bit line and bit line bar are pre-charged. So for the SRAM cell which is being accessed at this point, you can think of a scenario where your access transistor is now connected and the source of this access transistor is actually connected to VDD like shown here, right? So this gives you a little bit different scenario because originally we didn't have these access transistors on hold margin case, but in this case, this NMOS transistor would somehow affect your VTC, right? So let's think about that. So this is the first inverter, and originally what we had was VTC, which it would look like something like this. That's more familiar form, right? But now what we see is if your voltage on this node is lower, then you would have, let's say this voltage is like 100 millivolts, very low, and your VDD is like 1 volt. Then basically what you have here is you have VDS of 900 millivolts on this access transistor, and your VGS is also 900 millivolts. So basically what's going on here is you are injecting a lot of current through this access transistor. So if you have this current injection, basically you are pulling this up. Your output voltage V2 is being pulled up by this injected current. So although originally you had VTC look like this, when your output voltage is low, like this region, your VTC goes up like this. And that's because of this access transistor. When your output voltage is high, when your V2 is high, it doesn't really matter because your VDS and your VGS is very small, so you have less effect of this current injection. So that's why your VTC now looks like this instead of this. Okay, and same way for the other inverter, you also originally had this, but now your VTC moves like this, right? So what was the noise margin we had for hold case? That's the length of the maximum square that could be located inside the overlapping area, right? So in this case, the overlapped area got much smaller, you can see, right? And you can see the square itself is now much smaller, and your length of your side of a square is much smaller. So that means you have much smaller static noise margin for read operation compared to the holding case. Okay? So read operation is more sensitive to noise, basically. And that makes sense, right? You have a lot of current injected to your SRAM cell, so your internal node voltage could keep that voltage. Right, so that was the static noise margin for read operation. Then let's think about the